Welcome to my poster about variations of earthquake properties like seismicity, scalar potency, and focal mechanisms of earthquakes before, during, and after magnitude 7.1 Ridgecrest earthquake. The earthquake properties variations are compared with the 3D P-wave velocity model in this area and the sleep models of two major ruptures. To understand the preparation and termination of major ruptures and the interaction between major ruptures with the surrounding crust. First, were there any precursory signals before the major ruptures? We use the focal mechanisms in box AA prime to analyze the temporal variation of focal mechanism properties. For every adjacent 500 focal mechanisms, we calculate the percentage of normal faulting events, reverse faulting events, and the focal mechanism heterogeneity. There's a clear long-term decreasing percentage of normal faulting events before the magnitude 7.1 Ridgecrest earthquake. And here are several possible reasons for it. To eliminate the effect of fault orientation changes, we apply the same procedure to events in the coastal area where earthquakes have highly diverse fault orientations and high focal mechanism heterogeneity. We observe a similar trend with decreasing percentage of normal faulting events, suggesting that it might not be caused by the fault orientation changes, but caused by the regional stress changes. We check the effect of the horizontal stress orientation changes by comparing the p-axis azimuths before and after 2010. And we find a similar p-axis azimuths before and after 2010. For the faulting type of these focal mechanisms, there were much fewer normal faulting events in all regions after 2010. Here, the normal faulting are colored in red. So there's no clear horizontal stress orientation changes. The long-term decreasing percentage of normal faulting events is more likely to be caused by increase of shear stress. What caused the termination of magnitude 6.4 and the 7.1 earthquake? To check it, we compare the focal mechanism distribution before and after magnitude 7.1 earthquake. We find that the magnitude 6.4 earthquake terminates near the strong velocity contrast area and where the magnitude 7.1 earthquake initiate. From the aftershock distribution, we find that near the high velocity anomaly area, the focal mechanism show high degree of heterogeneity. So the area with strong fault and stress orientation changes and the strong velocity contrasts may act as a barrier, which can terminate the magnitude 6.4 earthquake, cause a stress concentration, and initiate the magnitude 7.1 earthquake. This can also explain the very shallow magnitude 7.1 hypocenter near the strong velocity contrast in the shallow part. The magnitude 7.1 earthquake terminates near the intersection with the Cottonwood Fault to the northwest and the Garlock Fault to the southeast, with abrupt fault orientation changes coinciding with the orientation of the intersected fault. How did the major rupture affect the surrounding crust? We check the temporal variation of earthquake depths, and we found many deeper than usual early aftershocks after magnitude 7.1 earthquakes, which are colored in red. And these deeper than usual early aftershocks are widely distributed in this area. We also check the event potency distribution normal to the mean fault in 5 subregions and find 5 to 10 kilometer wide aftershock zone in all of these 5 regions. And aftershocks also show highly heterogeneous focal mechanisms. All of this showing a complex failure processes associated with the volumetric damage zone, including the area below the nominal seismogenic zone. The lessons we learned from this earthquake can be further applied to other major earthquakes in Southern California and other areas.